All right, welcome everyone. Thank you so much to those who are here in person with us and also joining virtually. Really excited for this event and to have so many alumni come down, near and far, coming down to Indianapolis to view the total solar eclipse. I would also like to kind of introduce Bob Hull, who is the chair of the Alumni Association, just to say hi.
First of all, thank you all for coming today. This is really a great event. Anna is in charge of running our various regional gatherings that we've done throughout the United States. And I have to say that this looks to be the best attended event that she has scheduled this year. So we will encourage her to schedule eclipses more often.
We'll be traveling all over.
I'm sure that if you got the notice for this event, you're aware of all of the great things going on at Illinois Tech. And if you've got any questions, please don't hesitate to ask any of us.
Awesome.
Thank you for putting this together.
Oh, yeah.
Well, Jennifer and Anna, and
Thank you.
Yeah, thank you. I'd also just like to quickly recognize Michele and Kristen back here. They both work at CSO. So thank you to both of you for allowing us to use your space and helping us today. It's CSO is a beautiful building, and we're really excited to be here. All right. Well, I'm going to pass it off to Jennifer to introduce our featured speaker for today. I hope you enjoy our professor talk.
Hi, I'm Jennifer DeWinter. I'm the new Dean of Lewis College of Science and Letters, and I'm here representing the Department of Physics mostly, who has recently extended to Emily, our speaker today, a tenure track line so that she will continue to shape the future of our astrophysics program, which I'm delighted by. But first, I really want to thank Advancement, Anna especially. She was thanking everyone else, but honest to God, the number of times that I emailed her freaking out about something is pretty impressive. So all of Advancement has been amazing. And I just want to think about really quick what inspires us in science. And so as a dean of engineering, or not of engineering, at an engineering school, the dean of science, I often talk about science being like the place where innovation happens, because innovation requires discovery. But in fact, today tells us that it's not just an economic reason that we study science, that it's about something fundamental to being human. It's about wonder and mystery and surprise and delight. And so I'm so glad that you could join us here today to be part of this wonder and mystery and surprise and delight, which Emily is going to demystify for us a little bit. But what I want to do now is talk about Emily, because she is amazing. And I've learned so much about her this last year through a number of processes of working with her, because not only is she amazing, she runs our most popular major in Lewis College of Science and Letters, astrophysics. And so that has the most number of students coming into it. And of course, not all of them will go on to become astrophysicists, but they will go on to really interesting careers in which they understand looking at the complexity of the world in really concentrated ways. So Emily's research is not eclipses, surprise. Emily's research is in binary stars and what happens in matter transfers. So like when two stars come together, one of them starts sucking material off the other. It's very cool and very violent, and I love everything about it. And so she's been at Illinois Tech. She actually joined the same time I did. She reminded me. She seems to have been there much longer than me because she's had such a huge impact. Prior to that, she was at Northwestern, and even prior to that, she was in fact a fellow for the National Science Foundation. So without me talking anymore, let's start our talk.
All right, thank you all so much. I'm delighted to be here with you today. Just by a show of hands, can I see how many people have actually seen a total eclipse before? Okay. Has anyone seen more than one? Okay, so this is going to be the second for a couple of people. Okay, awesome. Let me see if I can find this. I am a stellar astrophysicist. So I really study stars, particularly binary stars. But today I'm going to be talking to you about eclipses and the sun. But of course, the sun is just our nearest and dearest star. So I'll highlight a little bit of the stellar physics going on that we can actually observe during a total eclipse. So we'll just start with the basics. Why is it that an eclipse occurs? Well, during an eclipse, the moon passes in front of the sun and casts a shadow onto the earth. And so you can see in this diagram, we are in the path of totality, which is this small shadow on earth where the entirety of the sun is blocked. There's also a much larger partial eclipse zone where you see some of the sun blocked, but not all. Has anyone seen a partial eclipse before? Okay, so a lot more people have seen a partial eclipse. If you have seen a partial eclipse, but not a total eclipse, you are in for a treat today. I think the difference between partial and total is not just like a few percent of the coverage that's different. It's really a totally different and really profound experience to see totality. So it's, you know, as evidenced by the number of you that have actually seen a total eclipse, these are pretty rare events. And it's not that they're actually rare overall. So we actually get, you know, total, or not total, but we get some kind of eclipse every year, maybe partial, maybe total. There are 2 different eclipse seasons. And the reason for this is that the orbits of the moon in the sky and then the sun in the sky don't overlap personally. They're actually, they're tilted by 5 degrees relative to each other. So, you know, from this diagram, you might think, well, every time we have a new moon, we have the moon right in front of the sun. Why don't we get an eclipse every time we have a new moon? And the answer is because usually, you know, the moon is a little bit above or below where the sun is. So we don't actually get an eclipse for every new moon. We get them only about twice a year during eclipse season when the plane of the moon's orbit crosses the planes of the sun's orbit and we get a new moon at that time. Now, even though we're getting eclipses a couple of times a year, somewhere on Earth, it's rare that they actually cross any given locality. So we are lucky enough today to be in the zone of a total eclipse. The blue on here are total eclipses. The red is another kind of eclipse called an annular eclipse. So the moon actually kind of moves a little bit closer to the Earth and further away from the Earth in its orbit. And we also move a little bit closer and further from the sun in Earth's orbit around the sun. And so sometimes in the sky, the moon and the sun are just exactly the same size. And we get a full total eclipse where the entire sun is blocked. Sometimes the moon is actually slightly smaller than the sun in the sky, and that's when we get an annular eclipse. We can still see the edge of the sun when the moon passes in front of it. And I think this is actually really one of the great cosmic coincidences, that our moon just happens to be exactly the same size as our sun in the sky. The moon was a little further away, a little smaller, we wouldn't get total eclipses. You know, if we were in orbit a little further away or closer to the sun would be bigger and we wouldn't get total eclipses. So we're really quite fortunate to live on a planet where this phenomenon can actually occur. It doesn't necessarily happen everywhere. So humans have been really enthralled by solar eclipses forever. And we actually have a lot of data from early astronomy. Astronomy is really one of the oldest sciences. You know, we have records going back, you know, into the thousands of BCs where people were actually documenting the motions of things in the heavens. On the left here, you see that there is this petroglyph that is actually at Chaco Canyon in New Mexico. Has anyone been there to Chaco Canyon? A couple people. It's not definitive, but a lot of people think that this petroglyph is actually a depiction of a solar eclipse that would have been visible in Chaco Canyon in 1097 AD. So almost 1,000 years ago here, we're talking, people have seen these eclipses and documented them. You can see on the right, this is a sketch of a 19th century eclipse that was visible from Spain. And it actually doesn't look too different than the petroglyph, right? Like you see this disc, you see all this swirly stuff around it. And this is what you guys are going to see during totality. I think this drawing will make a lot of sense when you go out and actually see what's happening out there in the sun today. So let's take a little bit of a closer look at the sun. Has anyone had the chance to look at the sun through a telescope before? Only a couple people. All right. If you do look through a telescope at the sun and magnify it, this is kind of what you're going to see. It's, you know, a nice yellow or orange disk. You can see there's these little dark spots on there. Those are sunspots. So those are sort of regions of enhanced magnetic activity on the sun. They will come and go depending on the solar cycle. So the sun has an 11-year cycle where magnetic activity ramps up and then decreases again. And at maximum activity, we see lots of sunspots on the sun. At minimum activity, we see only a few. We're actually quite close to solar max during this eclipse, which is interesting. And I'll talk more about that in just a second.
Pass this around.
Oh yeah, go ahead, pass that around the table. Beautiful.
This way.
So this is basically what the sun will look like if you look just in visible light at the sun. Now I'm going to show you a movie. And this is a movie of the sun taken with NASA's Solar Dynamics Observatory. And this is an image of the sun in ultraviolet light. And so what you're seeing is where you saw those sunspots before, you're actually seeing these kind of like bright regions and dimmer regions. This is related to that sunspot phenomenon. We're seeing regions of enhanced magnetic activity where the sun is a little bit hotter or a little bit cooler where it's dark. Hopefully that again.
Where is it?
It's in orbit.
Okay.
Yeah, it's in orbit. It's a space observatory. So the thing I want to draw your attention to is if you look right around the edges of the sun here, what do you guys notice going on there?
Flares.
There's flares. There's flares. So there's a lot of really interesting features in the atmosphere of the sun. So we call the surface of the sun that you're seeing in a picture like this, the photosphere. That's normally the surface we see. If we look in the ultraviolet, we actually get a much better view of the atmosphere of the sun. So above the photosphere, we have a layer called the chromosphere, and then above that, a layer called the corona. And one of the big mysteries about the sun, it's called the coronal heating problem. We know that the corona is extremely hot. The surface of the sun is about 6,000 degrees. The corona is over 1 million degrees. Wow. So how does that very tenuous gas in the atmosphere of the sun actually get that hot? We don't totally know, but we think the answer is magnetic fields. So you can have these dramatic magnetic reconnection events that launch solar flares. You're seeing some of that in this video as well, where you get these little flashes. You see material being ejected from the atmosphere. And so we think that it's magnetic heating processes that are kind of heating the corona up to this super hot temperature. Now, the really amazing thing about an eclipse is when you block out the entire disk of the sun, you block out the photosphere, what we see with our eye is the corona. So when you saw all that swirling stuff in that petroglyph or in that sketch, what was happening is ancient people were seeing this 1 million degree tenuous gas flickering all around. And that's what you guys are going to get to see with your eyes today, if it's clear. Hopefully we get a good view. Okay, so I want to tell you a little bit about the history of eclipse observations and just highlight a few really important scientific breakthroughs that have actually come with observing the sun during these eclipses. So this is an image of the sun that was taken in India in 1868. And you can see that it looks like there's this black disk. That is the moon blocking out the sun. And then you see this like kind of wispy gas all around the edge. So that is the solar atmosphere that they were actually able to image on a photographic plate in 1868. So this was one of the first eclipses that happened when we had actually developed pretty modern telescope technology. We could take pictures using glass photographic plates. And there was actually a new invention of a spectroscope. So here is an illustration on the left of an astronomer in, the mid 1800s using a telescope with this instrument called a spectroscope attached. And a spectroscope is basically a prism that will take the light coming from the sun and split it out into its component wavelengths. So you can see I have this little rainbow diagram here. If you attach the spectroscope to a telescope, it's splitting out all the light coming from the sun, and instead of seeing just integrated white light, you see that there are certain wavelengths of light that the sun is emitting more. And so right here, you see that there's this bright yellow line. It's at 588 nanometers. That is actually an emission line from the element helium. Now, in the 1860s, we actually did not know helium existed. And that is because it's a very light element. There's not very much of it on the Earth at all because it just escapes from the Earth's atmosphere. So there were all these experiments going on at the time, just kind of, looking at different elements, taking spectra of them to see where they emitted. Every element kind of emits in a different color. But no one knew helium existed. It turns out the most abundant things by far in our entire universe are hydrogen and helium. The universe is about 70% hydrogen, 28% helium. So we were missing a huge bunch of stuff there. And helium was first detected in the sun because an astronomer by the name of Jules Janssen took a spectroscope, a newly invented spectroscope, to India to watch the solar eclipse. During the moment of totality, he pointed his telescope at that tenuous atmosphere. That tenuous atmosphere is made up 70% hydrogen, 28% helium. So he saw this booming yellow line that was the emission of the helium, and he knew it didn't correspond to any known elements at the time. And that was the first discovery of helium. It took many years for it to be confirmed in laboratory on the Earth. It was first discovered in the sun, and that's why helium, helios for the sun, it's named for the sun. Major discovery that was brought about because Jules Janssen went to India to observe this eclipse. I know, thinking about this, like it's 1868. He went from Europe to India to observe the eclipse. So this was not a small journey. This was a major undertaking. And he had this major scientific breakthrough because of it. There is this great biography of Jules Janssen. And here's a quote from it. It says, his adventures in connection with his scientific expeditions bordered on romantic. At the time of the eclipse of December 22nd, 1870, so this is 2 years after the eclipse where he discovered helium, he was in Paris, besieged by the German army. It was the middle of the Franco-Prussian War, and Paris was under siege. But so determined was he to see the eclipse visible in Algeria that he escaped from the city in a hot air balloon. So he actually hot air ballooned over the German lines and landed and was able to get to Algeria. Unfortunately, he never observed the eclipse because there were clouds. So hopefully that puts in perspective any weather struggles we have today. Hot air balloon out of Germany. So I think this is a really interesting story because astronomers back in the day were really adventurers, traveling the world to see something like a solar eclipse. They were building observatories on the top of mountains, in the late 1800s. So you had to have a strong constitution to do the work of an astronomer in the late 1800s. Okay, so fast forward several decades. I think perhaps the most famous scientific discovery that came about from a solar eclipse goes back to this guy. How many people recognize this guy? We've got Albert Einstein here. So Einstein was working in 1905. That was his year where he published like the great majority of discoveries that you associate with Einstein. In 1911, he is working on his theory of general relativity. And he comes to the startling math, like he's working through the math, and he comes to this discovery that mass actually bends light. That's one of the predictions of his theory. And this is very important because it means general relativity is testable. It moves it from this kind of theoretical, kind of crazy stuff to like testable predictions that come out of his calculations. And so he starts writing letters to astronomers all over the world, explaining what his prediction is and asking for help testing it. So what you see here is the a copy of the letter that Einstein sent in 1913 to George Ellery Hale, who was the director of Mount Wilson Observatory, which is right outside Pasadena, California. It was one of the preeminent observatories at the time, staffed many, many prominent astronomers. And he writes this letter to Hale and asks, you know, I have this prediction. You can see his little sketch here. There's a circle there, that's the sun. And he's showing that his prediction is that a light wave ray will actually be bent around the sun by a measurement of 0.84 arc seconds. So an arc second, if you don't know, there are 60 arc minutes in 1 degree, and there are 60 arc seconds in 1 arc minute. So 1 arc second is 1/3600th of a degree. So a tiny, tiny, tiny shift, but measurable on the best telescopes at the time. So he writes to George Ellery Hale and says, this is my prediction, can we test it? And Hale wrote back and said, the only time that we could test this is during a solar eclipse. So you're gonna have to wait. So this is 1913. One of the first attempts to do this is an eclipse in 1914. There's an expedition planned to Crimea, but World War I broke out. The astronomers who were headed there to do the measurements were arrested in Russia, and their equipment was confiscated. And you know, then World War I is going on in Europe. A lot of, you know, Einstein is German. A lot of these preeminent astronomers are working in England or, you know, other localities that they're at war with each other. So there's not another chance for the astronomers to test relativity for another 5 years. Okay, so 1919 rolls around, and this is the eclipse that finally does it, finally is able to test relativity. I was actually kind of fortuitous because by this time Einstein had done some more calculations, actually published his full theory of general relativity, and had revised his measurement. Now he thinks that the angle is actually going to deflect by 1.7 arc seconds. So twice as much as he thought at first in 1913, and definitely measurable. So 1919 is World War I finally comes to a close, and an astronomer by the name of Arthur Eddington, who's working in Great Britain, organizes an expedition, sends 2 teams out, one to the island of Principe, which is off of the coast of Africa, one to a town in Brazil. And there's going to be this solar eclipse. You can see the map here shows the trajectory of totality. So they have 2 teams, 2 chances to measure it. They're hoping that there's no clouds, good weather, no one gets arrested, no one's equipment is confiscated, everything goes according to plan. But again, 1919, this is not a small expedition to send people to these pretty remote locales. They are organizing for a long time. They have to bring all of their equipment there well in advance, set it all up. And remember, totality is only lasting a few minutes. So they have to be ready to go when totality happens. And this is also an amazing feat of international cooperation. So this is Einstein with Eddington sitting together. Much later, this is in the 1930s. I believe they had not even met at the time that they were working together on this confirmation of relativity. And again, you know, cooperation between German scientists and British scientists. It was really an amazing triumph of scientific cooperation after a long world war. This is an actual photographic plate, scanned, digitized photographic plate of the observations that were made during this 1919 eclipse that actually confirmed that Einstein was right, relativity was correct. So you can see circled around the sun here. These are different stars. And they measured these stars and found that indeed they were 1.7 arc seconds off from where they should have been if they were not just behind the sun. So it was a powerful confirmation that Einstein was right. And this really took him from, you know, well known in physics circles, like profound work that he was doing, to he was a celebrity, and there were headlines around the world that his theory of general relativity had been confirmed. You can also see that during the eclipse, you see there's this big kind of, it's called a solar prominence, protruding from the disk of the sun in the upper right. So again, remember that all of this stuff that you kind of see haloing the disk of the moon, that is that corona, and you can see it's pretty spectacular. So beautiful picture just of the sun, but the actual science is contained in these faint stars that you can see around it. So during totality, you'll actually see the bright stars come out in the sky around the sun, and we can actually see stars that we normally couldn't because they're up during the daytime.
Might be able to see a comet as well.
Might be able to see a comet, yeah. Sometimes all sorts of stuff comes into view that's
There is
usually
one
hidden
there.
by the sun, yeah. Yeah, so here's a headline, 1919, The Times of London, Revolution in Science, New Theory of the Universe, Newtonian Ideas Overthrown. So these are the kinds of headlines that are going up once these eclipse observations are analyzed and published. And Eddington's measurements really decisively confirmed Einstein's prediction that the stars actually, the position seems to move because the light is bent around the sun. And we see the star actually move when it's behind the sun. So I think this is probably the most famous science that has ever been done during a solar eclipse. Hard to beat that, I think. Hard to beat confirming Einstein's theory of general relativity. Okay, so just in closing, I want to say a few things about what you guys are actually going to see today. So here's just kind of a time lapse showing you're going to start to see the moon passing in front of the sun as we go into the partial eclipse. And the sun kind of grows smaller and smaller, becomes a crescent. Then we have this beautiful experience of totality. The sky goes dark, that atmosphere around the sun comes into view. And then after a few minutes, we head back into a partial eclipse, and the sun becomes a crescent again, and then goes back to full. So we're going to get a chance to see both the partial and the total phase of the eclipse today. I brought a colander. This is a picture of someone holding up a colander during the partial eclipse. The partial eclipse, when you first go outside, in some ways it's a little anticlimactic. Like it starts, nothing feels like that weird. You start to see that the sun is maybe shrinking a little bit. I would encourage you to keep your eyes on shadows because we don't think about it very much. Like you probably think when the sun's rays come through a hole in the colander, you see a little circle of light on the ground because this is a circle. But actually what we're seeing, this is a tiny pinhole camera, and you're seeing an image of the sun on the ground. And as the partial eclipse starts, you're going to start to see that all of those little images of the sun turn into crescent shapes. So you may not have brought a colander as I did. You can also just kind of hold your fingers up like that, make a little pinhole camera yourself to make shadows on the ground. If there's any trees or anything nearby, you'll see that the shadows that are cast on the trees start to look really weird because the shadows start to be very strange looking. So keep your eyes on the shadows as the eclipse is starting. They start to look really kind of funky, and I think that's, as you build up to totality, like things start getting a little spooky out there. And one of the reasons is that shadows aren't behaving quite the way you're used to. Okay, so as we go into totality, there's this phenomenon that's called Bailey's beads. It's also sometimes called the diamond ring. And so at that moment of totality, as the moon is passing in front of the sun, the topology of the lunar surface, so there's all these craters on there, and that means the edge isn't totally smooth. And so you'll actually see these kind of little circles of light peeking out from behind craters on the moon that create this kind of effect. It looks like there's maybe jewels kind of right around the edge of the sun. So when you see Bailey's beads, that's a signal that this eclipse is starting. And you're starting totality. So this is just a beautiful moment when we go to Bailey's beads and the diamond ring. And then we see totality, and like I keep showing you pictures of it. No picture can do the experience of totality justice. It's really just like beautiful and strange. But you start to be able to see this coronal gas, and we see these kind of lines, this weird kind of sculpted shape of the gas in the corona. And what we're really seeing there is the magnetic field structure of the sun. So the plasma of the sun, there's a wind driving it off the surface of the sun, and it is actually entrained to move along magnetic field lines. So you'll see that the plasma kind of outlines where the magnetic field lines are located around the sun. A few features to just keep in mind. So we talked a little bit about prominences. So these are these kind of like bright loops of material jutting out from the surface. There was that really spectacular prominence in that image from the 1919 eclipse where relativity was confirmed. There's also structures called coronal loops. So these are little magnetic field lines that connect sunspots on the surface of the sun. So you'll see that there's these like kind of closed loops where there's plasma moving up along the loop and then back down on these coronal loops. There's something called coronal holes. So these are kind of like the dark regions in between the lines that you see on here. There's also these things called streamers. So these are open magnetic field lines where plasma from the sun is actually streaming away from the sun. So the sun is always sending out these charged particles of plasma, and they will come out and actually hit the Earth's atmosphere. So one of the things that we're really interested in studying during a solar eclipse like this is looking at this structure of the corona and actually sort of seeing what the magnetic field topology looks like, what the plasma is doing up in these highest layers of the sun. We have a lot of really great ways to observe these kinds of coronal features now. There's a type of instrument called a coronagraph, which basically puts a baffle over the sun. So it kind of blocks out the sunlight and a telescope can look at the atmosphere. But still, the best way to observe the corona, especially the lowest parts of the corona, is during a solar eclipse. So solar scientists who are really interested in the solar corona, they are very excited to be able to see this structure and take measurements of it. Okay, the partial eclipse is about to start, and I would be remiss if I did not put a safety disclaimer here. During the brief phase of totality where the sun is completely blocked, you can take off your glasses and look directly at the sun. In fact, through these eclipse glasses, you will not see anything if you don't take them off. So you can take them off, but during the partial eclipse, absolutely not. If you're looking at the sun, keep your glasses on. You can kind of look at the sun during the partial eclipse because it doesn't hurt as much as when the full sun is in view, but that does not mean that it's not blinding you. It still is blinding you. So keep your glasses on during the partial eclipse if you're looking at the sun. Only take them off during that brief window of totality. All right, is everybody ready to see it? Okay, I'm gonna hand it back to Anna and she'll tell us what to do.
I brought along a telescope with use it in hydrogen alpha, so
Awesome.
I can confirm that there was a prominence on it and solar. So
Beautiful, yeah. This is a great time to be seeing an eclipse.
That
We are close
at least
to max.
it was there 2 hours ago anyway.
Awesome.
Great. Well, thank you, everyone. Obviously, we're gonna start moving outside because I know that the partial is gonna start in a couple minutes. If anyone, here has questions, Emily will be around for a little bit, and so we can ask them out there, but we'll start moving everyone out. Thank you, everyone, for joining us virtually.
Thank you.
I think he's got a lot.